I was gonna say
kind
too.
of insanity.
Yeah.
Okay, so let's chit chat about where we're at in this journey. So Copernicus, remember, he was the first one that came out and said, "Hey, here's a valid argument for a heliocentric solar system." And if you think about it, even if you just look at observations, you could have figured out that there was something wrong. Well, this is what we talked about yesterday. So if here's the Earth, and all the planets revolved around us, then, including the sun, then the argument is like, why could we never see like a full Mercury or a full Venus like we do the exterior planets of, Mars, Jupiter, Saturn, that type of thing. And so it's like that by itself says, hey, something's wrong. Because if they're all orbiting us, then they should all have the same type of view. So Tycho Brahe has his own island, builds this great observatory, collects years and years and years and years of data. Johannes Kepler comes along and says, hey, I like this. I need the data. I'm on a mission from God. Tycho passes away, unfortunately. Dane says, I'm going to keep the family. Kepler goes mission impossible, background music, storms the castle wall, takes the books, runs, hides back to Germany, spends years crunching the numbers, comes up with his 3 laws of motion. And this is going to form the basis of the lab that we're going to start today and we'll finish up on Monday. So the first one, and these all kind of play out together, is the law of ellipses, okay? So remember, with an ellipse, how many foci do you have? 2, okay? And the farther apart they are, what do you know about the eccentricity?
It's wide.
Yeah, so the more eccentricity it has, the farther apart the 2 foci are. So what do you call an ellipse that only has 1 foci?
A circle.
A circle, okay? So the farther apart they are, and so they figured that Mars actually has a relatively large eccentricity, about 10%, and they figured that if that eccentricity had been much less than that, even within the limitations of Tycho Brahe's data, Kepler probably would have deduced that, they're probably circular, okay? But we got lucky, or he got lucky, because of the fact that it was had enough eccentricity to observe the fact that it was traveling in an ellipse. So the second one is the law of equal areas of equal times, and this is going to form the main basis of the lab that you're going to do today. So basically, if you come in here and you calculate these areas, and for the lab today, we're going to do like a 10-day period. It really doesn't make any difference, okay? Pick a point, like a month doesn't make any difference. So in 10 days, you're going to calculate an area that was swept out. And then over here, you're going to calculate another 10-day area. So here's your trade-off. When it's closer and you have a smaller radius, you have a bigger arc length, okay? It's going to travel through more degrees. When it's further out here, you have a bigger radius, but it's moving slower. So here's all for now I want you to remember about the ramifications of that second law. When you decrease that radius, you increase the velocity. When you increase the radius, you decrease the velocity. So what that means is that this planet is spending about half of its time speeding up, and it's going to spend half of its time slowing down, okay? Now, the third one is the mathematical one. And that's TA squared over TB squared equals RA cubed over RB cubed. Now, your Kepler. You don't have an iPhone. You don't have the internet. You don't have a calculator, okay? So what's the numeric value you're going to use every chance that you get?
1.
1. So here's what's important. In Kepler's mind, he was searching for ratios, okay? He thought there was a simple mathematical formula to describe the motions of the planets. He didn't know the distances. This was a ratio. So he chose Mars to collect a lot of data on. And the reason he chose Mars is, if you think about it, here's the sun, here's the Earth, here's Mars in its orbit, okay? So as Mars goes around its orbit, even from the Earth, the only time you won't be able to get any data on Mars is when it's directly behind the sun, okay? So most of the time, you might not be able to see a lot of Mars, but you're going to be able to see a lot, you're going to be able to collect a lot of data on it. So what Kepler did, he said, okay, let's compare the Earth to the Mars. So he had a lot of data on that. So what I always do personally is I always cross multiply. So I'm going to write that as TA squared times RB cubed equals TB squared times RB cubed, RA cubed. So here's the ramification. So if you look at period of the Earth squared times the radius of Mars cubed is going to equal the period of Mars squared times the radius of Earth cubed. Now, don't discount the significance of this equal sign in the middle, okay? It's a very simple idea, but it's hugely important. So what this says is, okay, these two numerically, I don't care what these numbers are. They both sides could be 1,000, 5,000, 321.4. I don't care. But the numbers have to be the same, okay? That's the ramification. The numbers have to be the same. Kepler didn't know the actual distances. So he said, okay, this is cool. So you know the period of the Earth and the radius of the Earth. Those numbers here, when we look at this on this comparison, period of the Earth is going to be like 1 year. Okay, that's cool. And then you're going to multiply that by the radius of Mars cubed, and then that's going to equal the period of Mars squared times the radius of Earth cubed. So since these sides have to be equal, something has to balance something out. So the only way that balances is if the Earth is going to have a shorter period, okay, and it's going to have a smaller radius. So to balance this out, because of the fact that these two numbers multiplied have to equal the same thing, the radius and period of Mars have to balance this out so that you end up with that equal sign. So if you're Kepler, you're going to let the period of the Earth be 1 year, because that's an easy number to work with. You're going to let the radius of the Earth be 1 astronomical unit. Because he didn't know the distance anyway. He goes, well, if I don't know the distance, let me pick a number. Oh, I'll pick 1. That makes sense. So what you're left with is this. So you can simplify this down as long as two of your values have a value of 1. So what you're left with is basically saying that the radius of Mars cubed is going to equal the period of Mars squared. So if you, like, let's say, for example, you know the radius of Mars and you want to solve for the period. Oh, I'm going to take the square root of this. So you would cube the radius, and then you would take the square root. Now, keep in mind, yes?
How do the units work on that? Like,
because technically, this is years, and technically this is astronomical units.
well, yeah, like how does, like, I don't know, astronomical units cubed and then the square root of that equal years? Is what
But what's implied within that is technically you're multiplying that by period squared. So technically the units are still there.
Oh, okay.
Okay?
Got it.
But they just kind of float in and float out because it simplifies down to that ratio.
Okay.
Now there are situations like, for example, when you get to this question on number 7, when you're talking about Venus, okay? So when you get to number 7, and you get a problem like number 7, and you're going, my God, I have no idea how to do number 7, okay? Lay this out. You have 4 variables. You have the period of Venus, you have the period of Earth, you have the radius of Venus, you have the radius of Earth. And it doesn't make any difference which one you put on top, it doesn't make any difference. But these are going to get squared, and these are going to get cubed. Now, if God wanted to make this simple, what could have been the simplest ratio that could have existed?
1 to 1.
A 1-to-1 ratio. In other words, if the period of Mercury was twice that of the Earth, the radius of Mercury would have been twice as far. Okay? If it's 3 times further, the period would be 3 years. That would have been the simplest ratio. It wasn't bad. It was still squares and cubes, but it wasn't, it wasn't like t to the 24th equals r to the 35th, okay? So it could have been a lot worse. It wasn't bad. So here's the decision that you have to make when you get to one like number 7. And there's going to be a question like this on the lab. So you're told that Venus has an orbital period of 225 days. Okay? Now, that's cool. There are 225 days. But if you're going to leave this in days, what do you have to use for the orbital period of the Earth?
Days.
Yeah, then you got to use that as 365 days. So this is a situation where it's the only time you will ever hear me say this in this class. I don't care what the units are, as long as they're the same. Okay? You can have kilometers and kilometers, astronomical units, astronomical units. I don't care. They just have to be the same because it's a ratio. Now, if you really want to make this simple, you can still let the period of the Earth be 1 year. But then you got to take the period of Venus, divide that by 365 days, and have that as a decimal fraction as part of the year. Okay? So you can still do this, but you cannot leave the period of Venus as days. You got to change that into years. So now, if you think about your answer to number 7, what does your answer have to be less than in terms of astronomical units?
1.
1, because it's an interior planet. Okay? So your answer to number 7 should start with a 7 as far as your decimal goes. Okay? Now, your answer to number 8 should be something around your age, maybe a little bit higher. Okay? Now, when you get to number 9, there's a couple of ways you can do number 9. And I don't care what you do. This is completely and totally up to you. It makes me no difference whatsoever. So again, you have to be in that mindset of Kepler, that you are trying to find a ratio. You don't know the numbers, you don't care, because you're just trying to find the ratio. So here's what you can do. Leftover notes from yesterday. So one option is that you sit there and go, okay, here's the Earth, here's the moon, and here's this satellite. Okay? So option number 1 is that you're told that the satellite is placed in orbit that is half that of the moon's. Okay? So one option is that you let the distance to the satellite have a numeric value of 1. I don't care what it is, I'm just going to let it be 1, because it's a ratio, it doesn't make any difference. So if you're going to let the distance to the satellite be 1, what's going to be the distance to the moon? 2. Okay, there's the distance to the moon. That's going to be 2.0. Your other option is that you let the radius of the moon be 1, then the radius of the satellite is going to be
1/2.
0.5. So you either use 1 and 2 or 1 and 0.5. It's up to you. It makes me no difference. It's going to be the same ratio anyway. It's not going to make any difference. Now the tricky part is that you're told that you want to find the period of the satellite as a multiple of the moon's period. So you don't know, I didn't tell you what the period of the moon is. So if you're clever, and you all are, what are you going to let the period of the moon be?
1.
And instead of 1 year, we're going to call it 1
Moon.
lunar year, or 1 lunar orbit, or something like that. So the only thing you're not going to know is the period of the satellite. Now, when you find the period of the satellite, is the period of the satellite going to be less than or equal to 1? Less than, because the satellite is inside the orbit of the moon. Okay? So when you get this answer, I'm just going to pick up a number. Let's say it's 0.4, and it should be kind of close to that. So you find the period of the moon to be 0.4. So how you want to write that answer is that you're going to say the period of the satellite is 0.4 times the period of the moon. Now, the beauty of it is then if I tell you, oh, the period of the moon is actually 28 days, Then you could just take that decimal, multiply it by the actual orbital period, then you would get the actual period of that satellite. Okay? We're good.
Yeah.
I have a question.
I find that shocking.
I know. I thought I should wait maybe until class.
Ask.
For one.
Dear Lord, you are not asking your buddy.
Wait on that one. My bad. That would have been embarrassing. Okay. For number 3.
Sorry, embarrassing.
I said, does this make sense? The Kepler's law only applies to objects orbiting the same object?
Orbiting the same center.
Oh, the same center?
Yeah.
Okay. That makes sense.
Wait, what?
And later on, you see why that plays out with Newton's laws.
Okay. Sounds good. That's all I had, I believe.
Okay?
One is just 'cause the tail,
Make
right?
sure on number 4 that if you're going to write a description, make sure that you have a good description, or a diagram might be better. So you don't have to draw a diagram, but a diagram helps. So, all right. Anything else? Going
Is this
once.
just the two?
Going twice.
Oh, I wanna ask. It's just the two, right? On number one.
So get that handed in.
Number 1? Yeah.
It's tilted toward the sun, right?
So Merle will stop you under here.
No, it's because of the...
I'm not looking.
Okay. So here's what we're going to do. We're actually kind of work through this whole thing kind of as a collective group.
Yes,
Kind of piecemeal.
So you can't be wrong, hopefully.
So here you've got yonder polar graph, okay?
I wonder if this is
And here's 0 degrees, and going around, there's 180.
Monday.
And so what we're going to do is we're going to look at the motion of Mercury through the prism of Kepler's 3 laws, okay? So first law of Kepler says, hey, it travels in an ellipse. So when you look at this, your graph should look something like
Oh,
this,
fire.
okay?
One second, I should have.
Slightly offset, okay? Now, if Kepler's first law was the law of circles, why would that task would have been much simpler?
Draw a circle.
Yeah, just pick a point, draw it around, okay?
Yeah.
Take a compass, draw a circle, boom, there you go. Easy, there you go, Mr. Burkin. But, not quite that simple. So, by virtue of the fact that it's not a circle, and it actually does look like an ellipse and not a squirrel or something like that. So the first question that you have is, looking at your graph, does the orbit support Kepler's first law? Explain. My answer says, yeah, it kind of looks like an ellipse. Oh, there you go. Now, the second law is much more difficult to do, okay? So in the second law, what we're going to do is we're going to find the area swept out by 3 different 10-day periods. And Mercury's orbit is only about 90 days, so 10-day periods is a relatively large percentage. 10-day period on the Earth, that would be a much smaller percentage of that orbit. With Mercury, 10 days is actually quite a big chunk of that. So the first 10-day period we're going to do together to make sure everybody's cool with how I want this process done. So we're going to find the area swept out between December 20th and December 30th. So looking at your data sheet, where is Mercury on December 20th? What's its radius and what's its angle? 0.309 and 65? Yeah. And then on December 30th, what do you got?
0.327, and then 126 degrees.
126 degrees. So what's happening here is that on December 20th, you're at about 65 degrees, which is about here, and then you're over here at 126 degrees. So what we're going to try and find is that area in between those 2 radii, okay? Now, there's a simple way you can do this and a complex way you can do this. Let's go with the simplified version. So what we're going to do, and I've got that formula there on number 3. We're going to use the area is going to equal theta over 360 times pi r squared. Now, the theta over 360 tells you what portion of the circle that you're looking at. So like if you wanted to look at half the circle, oh, that would be 180 degrees. Because that would be 180 over 360, which is 1/2 pi r squared. If you want to look at the entire circle, oh, that's 360 over 360, otherwise known as just pi r squared. So what this part tells me is that which portion of the arc length that we're looking at. So that just quantifies how much of the circle. Now, on the radius, that needs to be the average radius. So there's two ways you can do the average radius. One is that you add together the radii over all 10 days and you divide by 10, okay? That's too much work. So what we're going to do is we're going to simplify the process. What we're going to do is we're going to take the average of the two extremes, where it is on December 20th and where it is on December 30th. So, to get the theta part, if we take 126 minus 65, we get 61. So theta is 61. So what that means is that Mercury is going to sweep out 61 degrees during this 10-day period. Okay? Now, the radius. So somebody take 0.309. We're just going to take the average of these two values. So somebody take 0.309 plus 0.327 and divide that by 2.
318.
So we'll have 61 over 360 times pi, and what'd you get for that?
0.318.
0.318 AUs squared. Okay? Astronomical units. So this tells us how much of the circle that we're dealing with. Okay, not the whole thing. Okay, about 1/6 of it. And then this tells us that average radius. Okay, so this is going to at least get us close to what we're looking for. So somebody take 0.318 AU squared times pi times 61 and then divide that by 360. And I wanted 3 significant digits in scientific notation.
Did you guys get 5.38 times 10 to the negative 2?
Yep.
Nice.
What units?
AU squared.
AU squared.
Degrees?
That's the only thing that has. No, because you're dividing degrees by degrees.
Oh yeah, you're right.
Thanks. Okay. So, love it when I get that reaffirmation from my students. Wow. Makes me feel good. Okay. So here's what you're going to do. So everybody's going. So this is their first 10 day period. Everybody's going to use the same. So what you're going to do is you're going to go to your graph, okay? And so here's why I want you to do this, because eventually I've got to grade all these, and everybody's 10-day periods are going to be different. And if you want to use colored pencils and make this look cool, you can. If you just want to shade it in, that's cool. So what I want you to do is everybody's going to be the same. You're going to label this from December 20th to December 30th. Draw these lines, shade in that area. You don't have to shade it all the way to the edge of the graph. Just shade it to the edge of the orbit. Okay? Now, what you're going to do is you're going to come out here and you're going to pick 2 other 10-day periods. Okay? Now, keep in mind, this is everybody's 10-day periods are going to be different. So you have to make this easy for me to grade. So on your data table, oh, you highlighted the whole thing. Give me your graph. Give me somebody's data table who hasn't highlighted in orange the entire paper. Okay? So,
I don't know where my data table is.
So,
There it is.
let's say that you're going to do November 2nd through November 12th, okay? So, you're gonna do this, and you're gonna visually show me what's gonna happen on two locations. You're gonna come in here and you're gonna box in, oh, I'm gonna do November 2nd through November 12th. I don't care which, this is just an example, okay? Then, you're gonna come out here on November 2nd, you're at 241 degrees, and then November 12th, you're at 268. So what's gonna happen is that you're gonna come over here and you're gonna end up, it's gonna almost look kind of like a propeller. So you're gonna end up with 3 different regions. Be careful of picking a time that when you would cross over this 0 line. You can do it, but it gets a little bit tricky when you calculate that angle. So, because you've got to have like the degrees up to 0 and the degrees past 0. That gets a little bit, you can do it, but it just gets a little bit sketchy, okay? It takes a little bit more thought. So when you get done, I should be able to see on this graph which areas that you have shaded, and then on the other graph, you're gonna box in those 3-day periods. So when I go to grade this, if I need to look at it, I can see, oh, here are the 10-day periods that you picked. Okay, so stop that camera and make that. Find the average between the largest and the smallest radius through the entire thing. So somebody look through and find the smallest radius and the largest radius.
0.307.
That's the smallest?
Yep.
Okay. Largest, 0.4 something.
Yep.
0.467. So
Agreed.
somebody take 0.307 plus 0.467 and divide that by 2.
Isn't that just 0.16?
0.387 AUs. So what we're saying is that on average, okay, if you could draw this as a circular orbit, on average, that's the distance of Mercury's radius. Now, that's going to be the same for everybody. So
Wait.
what you're going to do on number 12, and there's some variation on how you can do number 12. We're going to calculate the orbital period of Mercury from Kepler's third law. So now the period of Mercury squared over to the period of the Earth squared is going to equal the radius of Mercury cubed divided by the radius of Earth cubed. Okay? Now, and I tell you on this one because Mercury is so close to the Sun that orbital period is going to be in days. So, this 0.387 is going to be the orbital radius of Mercury. What are you going to let the orbital radius of the Earth be?
1.
1 astronomical unit. Okay?
Can I borrow Mason Fresh?
Yes. You don't even have to bring them back.
Birthday boy.
So the period of Mercury is going to be your unknown. And then the period of the Earth is going to be 365 days, and that's going to get squared. So what I would recommend, personally, I would cross multiply to get rid of those fractions. And then you're going to solve for the period of Mercury, which should be less than 100. So stop the other game. Okay, so what you're going to see on 13, again, figure out where Mercury is on October 1st. Figure out how many days it takes to get back to that exact same point. Okay? Then you're going to add all those days up for October, November, and December. And then you're going to compare that to your answer for number 12 that you got out of this calculation from Kepler's third law. Okay? That's the whole point of this. Now, what you need to do on the graph for Monday, it's the easiest thing to do. You do this very quickly. So here's your graph. So over there on the top of page 3, here's your graph. There's the center. You need to find the single point where Mercury is traveling with its highest velocity. So where are you gonna find the point where it has its absolute highest velocity?
Shortest radius.
Smallest radius. So you're gonna find the point on that where it has the single point where it has its smallest radius. Then, obviously, then the slowest velocity is gonna be the single point when it is
Highest radius.
biggest radius. So you're gonna find the point where it has its biggest radius. Now, Mercury, just like the Earth, moves counterclockwise. So what you need to do next is label the region where it's slowing down and the region where it's speeding up. Okay? So you're going to come out here and you're just going to shade in and go, okay, hey, it's slowing down, it's speeding up, whatever you think that is. So that's the only homework that you have, is to go to that graph, find a single point where it's going fastest, find the single point where it's going slowest, then shade in the region where it's slowing down, shade in the region where it's speeding up. And that's all you got. Okay, so stop, go on the camera.